This recording is for Unit 4 practice tests and practice test, singular. I'm going to get to this one here in just a moment, but I noticed that from my homework recording, I forgot one very last question. So here is this one, also extra credit. So look at this beautiful space stamp sheet. You have to go to this website here and then enlarge the uncut press sheet, and you will see 4 images, and one of them says landing, probing, exploring, escaping, and figure out which of these verbs is wrong as you look at the images and the descriptions. I cannot post this here because the Postal Service actually doesn't allow, the United States Postal Service actually doesn't allow any of its images to post it anywhere. So, okay, let's get to the practice test. So here are just a couple of disclaimers. For Unit 4 practice test, especially look at the next time questions are posted in each lecture unit in the additional materials folder. That's true for all chapters, but especially for Unit 4. And then for the Unit 4 non-proctored exam, again, it's non-proctored. By the way, as you pay attention to the 75-minute time limit on the non-proctored exam, it's actually non-enforced, but I really like you to finish it within that amount of time. All right, let's get started on that practice test. So here we go. There's something on top here for this practice test, especially, okay, I just mentioned that, next time question, Unit 4, and then there's a little note about one of the computation problems at the very bottom. I posted it at the very top here because otherwise you might get it on the non-proctored exam, and then you would go there too, I guess. So anyway, question 1. So he finds it difficult to muster enough torque and so on, so he puts a rope on here, and now he's all happy. Will the torque be increased if he pulls as hard on the rope as shown? And the answer is no, because the lever arm, which is this one here, is just exactly the same. Now, if the whole thing was in a tight spot, you can make the argument, oh, okay, a rope little helps to get out of this tight spot, but it doesn't increase the torque. All right. Of course, let me go back to this one here. Of course, yeah, if you make an extension up here, so if you make this longer and then you grab on the top, now you have a longer lever arm. All right, when a skater brings in her arms when spinning, she increases her angular speed. The reason is that the angular momentum is being conserved. So as she decreases her rotational inertia, in order to conserve the angular momentum, the angular speed needs to increase. Okay, condition for mechanical equilibrium is that the sum of the forces acting equal 0. Another condition is that the sum of the torques also equal 0. If you look at my recording on the balancing the tray, that's the case there. There are forces acting. They're usually the weights of the objects that are on the tray that are pulling down, and my finger is actually pushing up. But at the same time, because I'm holding it off center, there's also torque. So the tray actually would like to rotate down and everything breaks and so on, but I'm holding onto it with my thumb, but my thumb has a very small lever arm, so that's why I have to exert a lot of force, and overall the torques are balancing it as well. Again, my tray example is a good one. Toss a baseball bat through the air. Well, don't do that inside, and it wobbles about its center of mass. I think there is a photo sequence in the book where you can see that, or you can find it online. Which will roll down faster? A can of regular liquid. Again, you can find it in one of my videos. I did find a second video. I posted as a comment to my video, and it's the regular liquid fruit juice, so the liquid one, that actually wins the race, and it's because the liquid doesn't have to rotate, so it has less rotational inertia, and as it doesn't rotate, it doesn't take up rotational energy, so therefore more energy of the original potential energy is left for kinetic energy, which makes it roll down. Okay, now these drawings, as you look at them, as I said, go to the next time questions, and here you see a bunch of them. There's a slide about the railroad tracks here and the different shapes. and then there's the answer. And there's the railroad tracks. And then there are the trucks here, and then there's the answer. And I think I skipped this one here, even though it's an interesting problem. Here's the one with the fruit juice. And here's another one with juices. And there's something here with the spheres and meter sticks. And there's James and the rope that doesn't work. And then there's the broomstick and so on. So look at these. They're posted in Lectures and Homework, Unit 4. Scroll down to the Additional Materials folder, and then it's at the very top, these next 10 questions. All right, so which will roll down faster, inclined plane, a hoop, or a solid disk? A solid disk, because the mass is closer to the center, to its center, therefore its rotational inertia is smaller, while the hoop has all the mass on the outside. A pair of upright meter sticks with the lower ends against the walls are allowed to fall to the floor. One is bare and the other has a heavy weight attached to its upper end. The stick to hit the floor first is and of course we're not tempted anymore of saying, well, heavy objects fall faster. No, they fall at the same rate. But the thing is that the bare meter stick has its center of mass right here, so in the middle, so it doesn't have far to fall, while the one here has a long ways to fall. And the other reason is that the rotational inertia of the weighted meter stick is larger, therefore it rotates slower. And so the bare stick is going to win. Similar explanation of that this one here, if you put it on your finger, if you put this end on your fingers, it's actually really easy to balance that one. I showed it in one of my videos. Because this one, because with the weight on top here, the rotational inertia is so large that it rotates very slowly, and you have a lot of time to compensate for when it wants to rotate off center, which is also why a hammer with the hammer head being on the top, you can actually balance it at its end. All right, the center of gravities of these three trucks parked on a hill are shown by the dots. Which trucks will tip over? Now, basically, we can say that if you're on a normal road, that probably truck C is the worst one to be packed. If you have like a shelf here and then you put the refrigerator up there or something like that, and virtually nothing here. That's on a normal road. But this is the way they're parked on this particular hill, and you have to see that here the weight on truck A pulls this way straight down, gravity, and it's off the pivot points, therefore this one is going to fall over. If you put the weight here, it's just inside, I think it's actually inside here, as I'm trying to draw this here with my left hand, just inside the pivot point, so that one is stable, and so is this one here. But it's only this particular hill, so truck A is the most unstable and will tip. Okay, a long explanation here for the helicopter, and you can assume that if I give a long explanation like that, it's probably true, but read through it anyway. Here's the one with the rollers, and you can see that in one of my videos where I do that. The cylinder is the moderately stable. The ones fastened at their narrow ends, which is this one here, is the least stable. That one goes off the rails right away. This one here stays really nicely in the rail. Even if you angle it a little bit, it just goes forth and back and nicely rolls down. Wobbles a little bit, but it's very stable. Pair of cups fastened at their white ends. And you saw that in the next time questions, and I also did that in the video. Broom balance at center of mass. If you sort the broom into two parts, the center of gravity, and which is here, the center of gravity apparently is here. Which part will weigh more? I did that in class one time with an old broom, and then my camera failed, so I actually don't have a video of it. What I do in the meantime is I took the sawed up broom and I put like a plastic tube over here, and then I just pull it apart and we put it on the balance and weight, and that's also in the video. And then the brush part is the heavier one, because once you sawed it apart, the brush part has a very small lever arm to approximately here maybe, so it must have a lot of weight in order to produce enough torque on the right-hand side before it's being sawed apart. Well, the meter stick, its center of mass is over here, so it has a long lever arm times a smaller mass in order to produce the same torque as the brush does. In the opposite direction, of course. Or the two are counteracting so that the torques before it is being sawed apart are the same. Okay, a 40-kilogram woman stands at the end of a 4-meter-long uniform plank. If the maximum overhang for balance is 1 meter, compute the mass of the plank. The plank's mass is 40 kilograms. I put so many different answers in here too. Well, don't make it so easy on this problem here. Notice that the woman has a mass of 40 kilograms, a lever arm of 1 meter, gravity of 10 meters per second squared down, which means she has 40 times 10 times 1, which is 400 Newton meters in a clockwise direction. That's how it wants to rotate. That needs to be made up for by a counterclockwise rotation from the plank, which is over here, and that needs to supply also 400 Newton meters. Now, somebody could argue that, well, each little piece here is rotating, pulling down, but one can also say, instead of computing for each little piece, let's just look where the center of mass is. And the center of mass is about here at half the plank's length, which is 2 meters. And since it is 2 meters, the center of mass is 1 meter off, which is the same lever as the one on the right-hand side. So the plank itself actually has the same lever. Therefore, it also needs to have lever arm. Therefore, it also needs to have the same mass, so that, again, you come up with 400 Newton meters. 40 kilogram mass for the plank times the 1 meter lever arm times gravity of 10 gives 400 Newton meters in a counterclockwise rotation. People are tempted to say, hey, you know, it has a 3-meter lever arm way out here. No, that's just absolutely not true. There is nothing there. There's a little piece of wood back here. That's it. But it's the entire length of the plank. Its center of mass is right here, and that's where the essential lever arm is. And I also have that in one of my videos, the one on the rotation experiments. And I think this is also, I think it is a next time question as well. When you pedal bicycle, again, long statement, long explanation here, so it's probably this one. And I was too lazy to come up with a stupid wrong answer, so I just put magic there. Long pole is more beneficial to a tightrope walker, and there is more rotational inertia, thus there would need to be a very large torque to create instability, and that is actually true, so there's actually the explanation here. Flight path of modern space vehicles is based on the work of Johannes Kepler. Kepler's laws, as you see them, the first of which is that planets or any kind of object that are orbiting around something are orbiting on ellipses. And then the interesting thing here is that when you look at the ellipses of the planets, they are very circular. However, the sun is off-center. I'm going to show you something here that I made. Let's see if this gets a little bigger. There we go. If you carefully look at this orbit of Mercury and you forget about everything else that's in the drawing here, then you will actually see, wow, this is really, really circular. And the same thing for other planets as well. Venus orbit is actually the most circular one. Earth's orbit, you can't even notice that it's an ellipse. It's a very, very slight ellipse, any one of these here. So when we say ellipses, that's actually true, but the orbits are so very little elliptical that they're almost circular. However, due to them being elliptical, that's why the sun is actually off-center. You can easily see that for Mercury's orbit here, that the sun is off-center. For the Earth, it's almost exactly in the center. Notice that this one is a little bit closer here, but here it's a little bit further, right? So here you have, in fact, if you look at the distance here, -1.01 maybe, and here it's 0.99. Well, that's still a diameter of about 2, while here, look, 1 and -1. It's also a diameter of 2, so the thing is really circular. I would have to drag it out to like the 3rd, 4th, 5th sig fig, I think it's the 5th, to actually see that there is a very slight difference. But the sun is actually shifted here, so here we have what's called the perihelion when we're closest, which is in early January, and here is the aphelion when we're furthest away, which is in July, which doesn't influence the seasons, topic for another day, because it's the tilt of the axis, which isn't shown in this one here. So we're actually closest in January, but again, it doesn't influence the seasons because that's when the northern hemisphere is tilted away from the sun. Okay, in any case, what I wanted to show here with this drawing is that the planet's orbits are actually so little elliptical. They are elliptical, but so little elliptical that they could be almost considered circular. And then there are others. There are moon's orbits. Neptune's moon Nereid is a very good example that is very elliptical, but many moon orbits are almost circular as well. It's just that the planet then is going to be off-center. Okay. Anyway, let's go back to the practice test here. So let's see, an Earth satellite is in an elliptical orbit. The satellite travels fastest when it is nearest the Earth due to Kepler's second law. So you can look that up. That's the conservation of angular momentum. That's the ice skater effect. And again, actually, the word elliptical is, well, it's mainly because the planet itself is not in the center, so that's why the satellite at times is closer to the Earth, and therefore it will orbit faster. The orbit itself might be actually very slightly elliptical. From Earth, one satellite appears to overtake another. A satellite that is in a smaller and quicker orbit is lower. That makes sense. It has to be closer. Then that's Kepler's third law. The larger an orbit is, the longer, of course, it takes to orbit. And when you look at the third law, it's not that one-to-one proportion, but it's the cube of the distance and the square of the period that are related. Okay. The orbital periods of the planets orbiting the sun depend on their distances from the sun. That's Kepler's third law as well, the one that I just described. One could say, well, why does it depend on the distance? And actually, not exactly. It actually depends on the mass of the sun itself. But of course, they are related. So it shouldn't say depend. It should say the orbital periods of the planets orbiting the sun relate to their distances from the sun. An object is placed exactly halfway between the Earth and the Moon. The object will fall toward the Earth at the same distance, with the Earth's mass being about 81 times larger than the Moon's mass. That means that the mutual gravitation between the Earth and the object is 80 times much as between the object and the Moon, and therefore it will, of course, fall towards the object. It says it's placed there. It doesn't say it's in an orbit, so I guess it will freely fall. The amount of gravitational force that acts on the space shuttle while in orbit is almost as much as the shuttle's weight on the Earth's surface. It's just a few hundred kilometers up, with a total radius of the Earth of 4,000 miles or 6,400 kilometers. So as it's just a little bit further up, the gravitation, of course, is almost the same as it is here. It comes out to 90%, 95% of what we experience here. Of course, the reason why they feel weightless is because at the same time as they're also in free fall, falling around the Earth, so to say. They have a very large speed, because otherwise they would fall towards Earth. Their speed is around 15,000 miles an hour or 24,000 kilometers an hour, which makes them orbit in about an hour and a half. And that is then actually, the gravitation is actually the centripetal force that holds them in orbit, and that their weightlessness is that they didn't lose their weight, it's that they're in free fall all the time. And that gets me to the free-falling runaway elevator. So somehow the cable ruptured, and here goes the elevator, and it falls down. And it's accelerated downwards. So the first statement is wrong. The acceleration is 9.8, acting on the elevator and on the person inside. The gravitational interaction, I'm trying to try this again here. The gravitational interaction with the Earth is 0. No, it's not. That's why the elevator is falling down, because of gravity. And the person as well. The Earth, by the way, due to mutual gravitation, is falling up, but the Earth has so much mass it really doesn't care. What is true is that the apparent weight is 0. So you're floating inside the elevator simply because both of them are accelerating in the same fashion, just the same as the astronaut and the space shuttle. And that's why they feel apparent weightless. And you put a scale there, and you cannot measure your weight. I mean, you're floating around. The scale is not going to work. So it's the apparent weight that is 0. You still have the same weight as you always do. The difference, of course, between the elevator and the space shuttle is that the elevator will impact very soon, and the space shuttle is nicely orbiting. It has tangential velocity and keeps it in its orbit. Which gets me to the moon. So the reason the moon does not crash into the Earth is that the moon has sufficient tangential speed. And when you do the calculation, then the gravitation from Earth pulling on the moon and moon pulling on the Earth, which is the same, that supplies the centripetal force that to keep the moon into orbit, and that also provides the amount of speed which it has to stay in orbit. By the way, the moon's orbit is elliptical, right? Well, look at this nice drawing here. This is the orbit of the moon, and if you look at it, it's really circular. Yes, the Earth is off-center. So if you measure this one here carefully, you will see that there is a slight, very slight elliptical. So the two diameters are not exactly the same. And if you measure this carefully, and I think you can also see it, that the Earth is actually a little bit off the center. But overall, while the orbit of the moon is a nearly circular ellipse, it's only a difference of 0.14%. The Earth's orbit around itself, the Earth's orbit around the Sun is even smaller percentage-wise. But with the Earth being off-center, that's why this distance here is 405,000 kilometers, while the distance on the other side is 362,000 kilometers. That's why you see the moon being quite a bit bigger when it's over here and quite a bit smaller when it's over here, but it's still an almost circular orbit. By the way, if you go to this Wikipedia page, you will see that I was the one who edited this part, and I also made the drawing. And I made the drawing after I noticed that someone on the German website had supplied virtually the same drawing. I guess this person here put the Earth a little bit on the right-hand side, so between this person's and my image, they're both rotated image-wise. Anyway, let's see. I'm going to go back here. Almost done with the practice tests. The Earth is currently accelerating towards the Sun. Centripetal acceleration. If the Sun collapsed into a black hole of the same mass, the Sun would never do that. Only heavy stars that have at least 10 solar masses, they could actually, or even 20 or more, they could actually collapse into a black hole after they went through their red giant phase, super red giant phase, and so on. But the Earth, it will eventually, after it becomes a red giant, then will push off its atmosphere into space, and the core will actually shrink to become a white dwarf, carbon white dwarf. So this is hypothetical. The Sun actually will not do that. But if it collapsed into a black hole of the same mass, the acceleration would be the same. The Earth would stay in the same kind of orbit in this hypothetical situation because the gravity didn't change since the mass, it says the mass is the same. Therefore, gravitation is going to be the same between Sun and Earth. Which is the most responsible for the ocean tides? It's the Moon and it's the Sun simply being there. Even though the Sun has a much larger gravitation between the Sun and Earth than the Moon does, tidal forces, because there are differential gravitational forces, they don't go with the square of the distance, but they go with the cube of the distance. That's why the Moon is more important than the Sun, and that's why, if you're familiar with tides, we're always looking at the tide books, and they give us the phases of the Moon, because that is what's related for the strength of the tides and what kind of tides we have throughout the months. And it so turns out that the Moon, but the Sun is not negligible. It so turns out that the Moon's tidal force is about twice as strong as the sun's is, so the moon supplies 2/3 of our total tidal force, and the sun supplies only 1/3. But the sun shouldn't be neglected, but the moon is actually somewhat more important. Then it's the varying distance, the moon and the sun, and that's a variance in their gravitation. And then it's also a tilt of the Earth's axis. So there is a number of reasons, but this here is the correct order for the first 4 reasons for how do we determine when the tides are the strongest. Main reason ocean tides exist is that the pull of the moon is greater on oceans closer to the moon and less on oceans farther from the moon. Unfortunately, when it gets to tides, if you Google that, you come up with a lot of wrong explanations. I think I do have a link to Donald Simonek's website posted, and go there, and he gives the most comprehensive one. The one on Wikipedia is also very good. As soon as you find the word centrifugal force on a website or in a book that tries to explain tides, just throw it away. It's wrong. It has nothing to do with centrifugal forces. It boils down to the gravitational force between the moon and the Earth, and the gravitational force being stronger on the side facing the moon and being weaker on the side facing away from the moon, because it's further away. It's 8,000 miles further away. That produces the tides, nothing else. And of course, the sun does the same thing on the Earth. The Earth is closest to the sun in January, which accounts for the fact that the highest high tides occur in January. That's kind of what I said here, the varying distance, moon and sun. That plays a role. It's very slightly, but if you actually plot it throughout the years, the highest high tides, you will come up with early January. Let's see. Best time for digging clams is when you have a low tide, so when moon and sun are aligned so that they pull in the same direction. Even if they're opposite from each other, still pull in the same direction, producing high tides where they are, and then you have extra high tides, but then also you have extra low tides, and that can only happen when the new moon if it's a new moon or a full moon, and that's when moon, Earth, and sun are all aligned. All right, one more, 2 more maybe. A bullet fired horizontally from a rifle begins to fall as soon as it leaves the barrel. In fact, it would also like to fall while it's inside the barrel, but the barrel, of course, supports it against gravity. But as soon as it leaves it, it will start falling down, which is, if you want to shoot at a target that is horizontally away from you, you actually have to aim higher. Because depending on how far the target is, it will fall down appreciably. That's also why the baseball player, by the way, is standing on a mound, so that he can throw horizontally while the ball is actually falling towards the pitcher. I'm sorry, that is the pitcher. Towards the batter is what I meant to say. An Earth satellite is simply a projectile freely falling around the Earth. Yes. Earth satellites are typically at an altitude of at least 100 kilometers so that they're above the Earth's atmosphere. Yep, so that friction doesn't slow them down. They're still a little bit out there, but depending on how high they are, how much atmosphere there's left, they may be slowed down very little that it's negligible. So that they're outside of Earth's gravitational field? No, definitely not. Just because they're orbiting doesn't mean that gravity is gone. Of course it's not gone. It's there. Gravitational force depends on the distance that you are. So it's weaker, but in fact it depends on the square of the distance, but it's not gone. It doesn't turn itself off, by the way. That's the answer to that last homework question that I forgot in the earlier recording on the homework, where they made a big blunder in there in one of the panels that they have on there. Communications of weather satellites always appear at the same place in the sky, hovering over the same point on the Earth's equator. Is because these satellites are placed in an orbit where they're orbiting the Earth with a 24-hour period. In the meantime, I did fix it. It's actually 23 hours, 56 minutes, 4 seconds, because it needs to match the Earth's rotation. And here, this is from the test being, they were just saying 24 hours here because that 23 hours, 56 minutes, 4 seconds is really close to 24 hours rounded. And then, of course, the computation problems, those are the ones that you will find in the recorded problems. And that's it for the recording on the practice test. And this time around it was a little longer because I kind of used it to lecture as well.